Hello, I'm Mikhail Dvorkin, ICPC 2007 gold medalist, and today, in order to show you some tricks and practices in using Kotlin for competitive programming, I will solve problem G, 2 IP cameras, from Kotlin Heroes episode 4. Here is the IntelliJ IDEA window with the educational plugin included, in which I opened the Kotlin Heroes episode 4 and problem G and its statement and the template for coding. Let me guide you briefly through the problem statement. There are two IP cameras that make photos periodically. That is, each camera has some moment of time where it starts and is making photos with a fixed period. The starting moments can be arbitrarily chosen by us, but the periods have to be from the set of the possible periods given to us in the input file. And the task is to select the starting moments and the periods for both cameras in such a way that all the moments of interest x1, x2, and so on, xn given to us in the input file are covered by at least one of the cameras. Or, of course, if there is no such configuration to fulfill all the interesting moments, then we should print to the output that this is impossible. I invite you, if you have the opportunity, to pause the video and to think about this problem by yourself. But now let's talk about the solution to this problem. Well, there are hundreds of thousands of possible periods for the cameras, so we cannot iterate over all the pairs of periods for camera 1 and camera 2. But the key idea is to try to narrow down this search by narrowing down the possible set of periods for one of the cameras. That is, consider moments of time number 0, 1, and 2. At least two of them should be covered by the same camera. So there is a camera that covers moments of time number, for example, 0 and 2, and therefore the period of this camera should be a divisor of the difference of these two moments of time. And since the number of divisors of such an integer is not so large, there is not a lot of periods that we are to iterate over. So we will consider moments of time with indexes 0, 1, and 2, select those two of them that are covered by the same camera, take the difference of these two moments of time, and only consider the periods for this camera that are divisors of this difference. For each period, we already have a lot of moments of time covered by this camera, and we need to make sure that all the uncovered moments of time are fulfilled by the other camera. So there are some uncovered moments of time, and we are to select the period that can cover all of them. Well, these uncovered moments of time should have the same remainder modulo the selected period. And even better to say this is that the differences of all the uncovered moments of time should be divisible by the selected period, which we'll be able to find in a quite fast time. This is the brief mathematical overview of the solution, and we'll see more specific details when we will be implementing the code in Kotlin. Let's start. I'm going to write the code from scratch, as if I have no pre-written code snippets to help me. So let's start by reading the input data. Let's take the first line. It contains the number of periods and the number of moments, but these two values can be taken from the arrays themselves. So I don't really want to store them into variables, and I just read this line and ignore it. Let's now read the actual data, the possible periods. I take the line, and it's definitely not null because the jury promised me that. I split it by a space character receiving an array of strings, and I don't want to work with arrays of strings. Let's rather work with array of integers. So I map them all to integers. Well, this looks like a very useful snippet of code. Let's extract it into a method that I will call readInts so that I can reuse it in order to read the third line with the moments of time. Now let's think about the final answer. It will be either yes with starting points and periods for the two cameras, or no. It looks like it's a good opportunity to use nullable types here. So I will implement the solve function that I will call and where I will implement the entire solution. And from this solve function, I will receive the 4 numbers that I'm going to output, or null if there is no such 4 numbers. In case of null, let's print no and finish the main method. Otherwise, I have the 4 numbers received from the solve method, and I can output them in a neat way that is desired by the jury. Now let's implement the actual solution, the solve function, that takes 2 arrays, the possible periods and the moments of interest, and returns the list of 4 numbers, or null if we haven't found an answer. So it's a nullable type. I will now iterate over I and j, which are the 2 moments of time that were taken by the first camera. So out of moments of time number 0, 1, and 2, at least 2 are taken by the first camera, and I want to iterate over all such pairs of I and j. One of the possible code snippets would be to iterate over I, which is, for example, the smaller index, and then iterate over j, which is the larger of the 2 indices, so it's larger than I. It's possible, but let's try another one, the funny one. It's really easy to make a mistake in these intervals in the lower or upper bounds. So let me iterate over the other variable k, that is the one that is not I and not j. It's somewhere inside 0, 1, 2, and then I and j are the numbers out of 0, 1, and 2 that are not k. I use multiple assignment here, and it's quite readable, I think. Now let's find the period for the first camera. It is among all the possible periods, and it is such a period that the moment number I and the moment number j have the same remainder modulo this period. So let's calculate the remainder of moment number I and moment number j, and if they have different remainders, then this current period is definitely not interesting for us, so it can continue to the next period. Otherwise, for this period of the first camera, we want to find a possible period for the second camera that covers all the uncovered moments. So let's find these uncovered moments. These are the moments of interest that are not covered by this first camera with this remainder. So these are the moments that have other remainder modular. We want to find whether there is a period for the second camera that allows us to cover all these uncovered moments. When some period is suitable, when all the differences between the neighbor elements in this array divide by this period. But if we check all the periods of second camera versus all the differences, then this will be a quadratic time and definitely not fit into time limit. So we should do something asymptotically better. We want to reformulate this property of a good period. All the neighboring differences should divide by this period. Well, this is true if and only if the greatest common divisor of all these differences divide by this period. So we can calculate this greatest common divisor of all the difference in linear time and then find a period for the second camera that is a divisor of this GCD also in linear time. Not quadratic at all, but linear. But before calculating the GCD of all the differences, let's think about the case when there will be no such differences. For example, if the amount of uncovered moments is either 1 or 0. Well, in this case, we are talking about the GCD of an empty set. And mathematically speaking, it's okay to define the GCD of an empty set to be 0. And we will be fine with this definition. So we can start with the initial value GCD equal to 0 and update it with all the differences, receiving new and new GCDs, including these differences. It looks like the built-in fold function, so let's code it like this. I take all the uncovered moments and I want to receive the array of all the differences between the neighbor elements of this array. This is the zip with next method, and I want to pass to it the function that will calculate the difference between the neighbor elements. But let's remember that this function is a build function minus, and having done that, I can simplify the syntax to zip with next using this minus function of the int type. And now with this array of the differences, I can make a fold function starting with the 0 and using each new difference to calculate the GCD of the previous result and this new difference. This will be a GCD function that I am yet to implement, and I can simplify this syntax in the same manner to receive the GCD of all the differences in one variable. And it will be 0 if there are no such. Let's implement the GCD function. One of the possibilities is to remember that in Java Virtual Machine we have a big integer class with GCD already implemented. So I can turn A to a big integer and calculate the GCD with B as big integer and then return to the int type because I know that the result definitely fits into the int type. That's possibility number 1. And another possibility is to implement my own recursive GCD implementation, which goes the following way, as I hope many of you know. If the first argument is 0, then the answer is definitely just the second argument. And otherwise, we can take the second argument modulo this non-zero first argument and the first argument. Please note that this GCD function of 2 zeros gives us a 0. And it's worth mentioning that the result of this function is a call to the same function itself. So this is an example of something called tail recursion, which will allow this to execute much faster. Now, in the linear time, well, honestly speaking, except for the GCD calculation, we have calculated the GCD of all the differences. And we are just to find whether there is a period for the second camera that is a divisor of all these differences and therefore is the divisor of their GCD. Let's use a simple linear search to find the first period that is indeed a divisor of this GCD. And if there is no such period, then there is no way to fulfill the uncovered moments, and we can continue because this period for the first camera is not interesting to us. Otherwise, the period for the second camera is not null, and we have found the correct periods for the first and second camera. So we can now calculate the phases, the starting points for both cameras. The phase for the first camera should be such that it covers moment number I and moment number j. So basically we're speaking about remainder of these moments modular period. But if we just write remainder modular period, the problem is that in the output they didn't allow us to use the phase equal to 0. So we have to adjust our formula to make it a non-zero starting point. We can do it using simple math like this. Well, it looks like a useful code snippet for calculating the starting phase, knowing the remainder and the period. So let me extract it as a method that I will reuse very soon, because I want to calculate the starting phase for the second camera, which is such a starting moment that it will cover successfully all the uncovered moments by the first camera. But if the array of uncovered moments is empty, which is possible, we can start with any starting point for the second camera, for example, a 0. Now we have calculated the phases and the periods for both cameras that work for our test case. So we can return these 4 numbers as an array from our solve method. So what have we done overall? We have iterated over I and j being the 2 indices of interesting moments out of 0, 1, and 2 that will be covered by the first camera. And for this I and j, we have iterated over all possible periods for the first camera covering these 2. And we have found the possible period for the second camera covering all the uncovered moments. Therefore, if we haven't found any 4 good numbers during these iterations, there is no way to cover all the moments with 2 cameras. And by our convention, we are to return null in this case overall. Now I can run the local tests to make sure that my outputs look really nice. Unfortunately, my outputs don't coincide fully to the outputs from the problem statement because there are several possible answers to each input, and if I print some suitable for numbers, it's also okay, but it doesn't coincide to the sample. I can now submit this code to the system, but unfortunately this very code receives the verdict time limit exceeded. And here is why it happens. Think of the number of possible periods of camera 1 that we are iterating over. This is the number of periods that are divisors of the difference between moment I and moment j. So if the jury gives us integers for moment 0, moment 1, and moment 2 that have a difference with very many divisors, we are going to iterate over a very large amount of possible periods. So let's design a trick to oversmart the jury that can give us such a test case so that they won't be able to make us iterate over a lot of periods for the first camera. Let's select the 3 moments of time that we are working with, not as the moments of time with indices 0, 1, and 2, but in some smarter way. One of the possibilities would be to select these 3 moments of time randomly out of all moments of time. But this will make my solution non-deterministic, so let's switch to a deterministic possibility. That is, let's take the 3 moments of time such that the difference between the first of them and the third of them is as small as possible. This way, if there are little moments of time overall, then our solution will be fast because the test case is small. And if there is a large number of moments overall, then we will find the 3 consecutive moments with not so high difference between the first and the third of them, and therefore the number of divisors of this interval will be less than in the previous case. So I want to find the index such that the difference between the moment at this index plus 2, and the moment with this index is smallest possible. I iterate over all possible indices and find the index with the minimal such value. And this is high time to remind ourselves that the number of moments in the input file can be less than 3. It can be a 2. And all our previous thinking was using the fact that there are at least 3 moments of time in the input file, which is not true. So let's fix it right now. In the case of 2 moments of time, our min by or null method will return a null because there is no such index at all. And in case of this null, we can return something special for the case of 2 moments of time. To return something special in case of a null, we use, of course, the Elvis operator. And the answer in case of the 2 moments is to use any periods for the cameras, for example, the periods number 0 and the moments of time to start the cameras such that the moment number 0 is covered by camera 1 and moment number 1 is covered by the camera 2. So we have covered the case of 2 moments of time, and now we have the wonderful index that is to be used in case of 3 and more moments of time. So let's use the triple of indices from this index to this index plus 2. And we will use this triple instead of indices 0, 1, and 2 that we used initially. We can submit this code to the system, and with the last smart trick, this code gets accepted. Thank you very much for watching this video. Enjoy competitive programming and enjoy writing in Kotlin. Good luck!